Now we're getting somewhere. Okay, so, question is, you get this polynomial, and I'm asking the question, how big does x gotta be so that x cubed is a whole lot bigger than 15x squared? Okay? Okay? So, ask me a number that's easy to square. People give me 2 or 3 or 6. Well, they're easy to square, fairly easy to cube, right? But what's even easier? 10. Round numbers. So, 10 cubed is 1,000, and 15 times 10 cubed squared is 1,500. Well, okay, 1,000 ain't even bigger than 1,500, right? So 10 probably ain't big enough.
Right.
Okay? So what do you want to try next? Okay, we'll try 100.
Oh boy.
It doesn't take too long to get.
100,000, a million.
It doesn't take too long before this stuff starts giving you big numbers. Okay, 100 cubed is 1,000,000. Okay? And 15 times 100 squared is 150,000. Okay? Now, what do you mean by a whole lot bigger?
Larger.
Well, this is 850,000 bigger than that, and 850,000 is a lot, unless you're talking about viruses or something. Probably shouldn't talk about viruses right now. Okay?
I mean,
Corona.
Yeah, corona. Yeah. That can get pretty hairy.
Virginia doesn't have cases.
So, especially for people my age, that's real good for old people. And you know. Okay, well anyhow. So, that's bigger. A better indication of how much bigger is how many times as big. So, x cubed is more than 6 times as big as 15x squared, right? Well, by that comparison, it's bigger. Would you call 6 a whole lot bigger? 6 times as big, a whole lot bigger? No, that's not a whole lot. 6 is a number we can easily understand. Okay? X cubed is 1,000,000,000.
Oh.
And 15x squared is 15,000,000. We're getting up into numbers, especially billion, they're kind of hard to understand. Okay? So, now to find out that x cubed is more than 6 times as big as 15x squared, I divided 1,000,000 by 150,000, right? So I divided x cubed by 15x squared to get that 6. It's actually close to 7. It's more than 6. Okay? So it's more than 60 times as big. Okay? Well, 60 is quite a bit more. And we start to see a progression. If x gets 10 times bigger, then this ratio of x cubed to 15x squared gets 10 times bigger, right? Okay? So, I don't consider 60 to be big enough. If x is 1,000,000,
I did fine. Let's see. I made it. You can't find it.
okay, I didn't write that out quite right, but you get the idea. X cubed over 15x squared equals, is more than 60,000. So now we're going to say, okay, it's a whole lot bigger. And if you don't think it's a whole lot bigger, you can make up a number here that makes it a whole lot bigger. You decide how big a whole lot bigger gotta be, and you can make it happen, right?
Anything's possible.
Okay? Make sense? Okay. And I'm not going to write it down, but it should be pretty clear that it's also going to be one whole lot bigger than 17x or 4, right? Okay? If it's a whole lot bigger than 15x squared, it's a whole lot bigger than 17x. Okay? Okay, well now we want to do this. Well, for large x values, this is this thing is pretty much the same as plain old x cubed. Because if x is big enough, these things don't make a hill of beans difference in how big this is. If x is 1,000,000, then if you compare this to this, they're only going to differ by 1 part in 60,000 or so, right? So if you had a graph where the x's are big, the graph of x cubed and the graph of x cubed minus 15x squared minus 17x plus 4 would be practically identical. They only differ when x has smaller values. Okay? So we have this picture. Of here's a graph of x cubed, okay? And our graph of x cubed plus 15x squared minus 7x plus 4 is probably going to have zeros in there somewhere, okay? Which means you can have the kind of thing we've seen where the graph kind of wiggles a little bit, right? Okay? So what I'm saying is that this graph, this will be x cubed,
That's going to be right.
and this graph
Yeah, but I can't wait.
Might do something like this. Actually, I did a little glitch there that doesn't work.
Yeah.
Just smooth that out a little bit. Okay? So this graph might wiggle a little bit here in the middle near the zeros, right? Okay? So,
Hello. Give it back.
so I say that this polynomial is going to be pretty much the same except for small x, where it might just wiggle a bit. Okay? And what we've seen from graphing polynomials in the form x minus this and x plus this and x minus that, and hopefully we've done a lot of that, is that, okay, for cubic polynomials, that's as much as they can factor. They just have an x plus this and x plus this and x plus this, and some of the pluses might be minus, might be negatives. Okay? So you're going to have at most 3 zeros, and the graph is going to have at most 1 complete wiggle. Okay? Make sense? So this graph has just 1 complete wiggle. Okay? And that's the most you can have for an x cubed function. They don't have to have a wiggle, although you do have to level off and then go back up. Okay? That's how polynomial of 3rd degree works. Because any polynomial like this can reduce at most to 3 linear factors, or 1 linear factor and 1 quadratic factor that doesn't reduce. Okay. Now, if you have a polynomial like this, okay, and you multiply that out using the distributive law, the highest power when you expand it is 4, right? In other words, if this is p of x, it's x to the 4th plus a bunch of stuff. And that bunch of stuff doesn't matter when x gets big. If you let x get big enough, x to the 4th overpowers all the other powers. That's why you call them powers, okay? X, of course, overpowers all the other powers. So your graph is going to look like this. Now the fourth power function looks a whole lot like a parabola, but it's a little more squared off down here. So this is your graph of x to the fourth, and your graph of p to the x. How many wiggles is it going to have? Well, you've got 4 zeros. You've got negative A, negative C, negative B, and negative D.
We have at most,
I'm sorry?
we have at most 4. Not having to have 4.
It depends on how you, what you call a wiggle, and it's not a mathematically standard term. Could be like this, right? Or, you know, of course, it's going to be measured by this. You turn this upside down, and it's, you know, you have a negative in front of the x to the fourth, right? A positive in the x to the fourth would have to look like this. So what it comes down to is your p of x is going to pretty much be the same as x to the fourth. But down here someplace it could have some wiggles. It could come down here, wiggle up, wiggle back down, then wiggle back up, and better come over here and eventually join this one. Okay? So come down, it's going to look something like this over here, okay? I didn't draw it very well. And of course, you know, we might have a scale here where this is 1,000 here and this is 1,000, right? And then you got numbers up here in the trillions, okay? So it could be like that. Does that make sense? From what you've seen, you understand that this will have 4 zeros, negative A, negative B, negative C, and negative D, which will be in some order. We don't know which one's bigger, which one's smaller, but they'll be in some order down here. Okay? That doesn't have to look like this, because of course it could factor differently, but you can't get more than 4 zeros, which means you can't have more than 4 turns. 3 turns. Turn, 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 right? So instead of wiggles, we really want to talk about turns because it's ambiguous what a wiggle means.
The wiggles.
But from what you already know, you understand how these graphs can turn. So that's kind of the terminology we'll use. Okay? Now, I'm going to post some videos. I'm going to post some videos with what you should know. For the midterm, I'm going to talk about that. I don't need to talk about it on camera.